Determining exactly what organic compound we have is important and complex as there are so many possibilities. You already know about the bromine water test for alkenes. To test for an aldehyde, we use Phelan solution, which when warmed produces a brick red precipitate in the presence of an aldehyde. No such change occurs with ketones. Or we can use Tollin's reagent, which forms a metallic silver film on the inside of the test tube when an aldehyde is present. Carboxylic acids react with sodium carbonate to produce CO2, which will turn lime water cloudy. Of course, test tube reactions only get you so far. Mass spectrometry allows you to determine the relative mass of a substance, including the atoms it consists of, as it also gives you the relative abundances in the compound. This can be used to infer the molecular formula, or the empirical formula at least. As the same atoms can be found in different molecules, we need something better if you want to know what functional groups we have. Enter infrared spectroscopy, which involves firing varying wavelengths of infrared, which are absorbed by specific bonds within molecules, producing characteristic absorption spectra depending on what functional groups are present. Transmittance is on the y-axis, so the lower the graph goes, the more that wavelength has been absorbed, showing that there's a specific bond present. However, we have wave number on the x-axis. This is just the reciprocal of wavelength in centimeters, so the unit for wave number is centimeters to the -1. Yes, sadly, you need to be able to spot these characteristic peaks, their shapes, and what wave number they occur at. On the rightmost part of the graph, you have lots of little peaks that tell us more about the specific molecule. This is called the fingerprint region. You don't need to learn any patterns here, thank goodness. NMR, nuclear magnetic resonance, tells us the most about a molecule. The process is really complex, but put simply, a magnetic field is applied to a sample, causing the nuclei spin to align with or against the field, which enables them to absorb radio waves of specific wavelengths, causing them to resonate. In fact, it's very similar to MRI machines in that regard. The x-axis has chemical shift on it, which is a bit of a funny one, but it is related to the frequency of radio waves absorbed. Chemical shift is measured in parts per million, ppm, relative to the molecule tetramethylsilane, which we say has a chemical shift of 0. That's because the 4 carbons are in identical environments on it. That is, it doesn't matter which you look at, they're bonded to the same atoms. You could put yourself in the shoes of one of these carbons, look around, and you couldn't tell which one you were. So we have a very defined single peak. Same goes for all the hydrogens too, so we use it for both types of NMR. Carbon-13 NMR analyzes what environments the carbons find themselves in as they exhibit chemical shift. It only works for carbon-13, but this is fine because this isotope is always present in a sample at around 1%, and NMR is very sensitive. Carbon environments near to an oxygen are shifted to the left, as oxygen is very electronegative. For any molecule that we're testing that isn't symmetrical like TMS, we see peaks for the different carbon environments. Let's look at isomers of dinitrobenzene. For 1,2-dinitrobenzene, how many different environments are there? 1, 2, 3. There are 6 carbons, but there are only 3 distinct environments. We could therefore draw a line of symmetry to show this. That means that we should see 3 peaks on the NMR. What about 1,3-dinitrobenzene? The line of symmetry is now here. The carbons on the line of symmetry are in different environments, so altogether we have 4 different environments, so 4 peaks. 1,4-dinitrobenzene, it has 2 lines of symmetry, showing that there are only 2 different carbon environments, 4 of one, 2 of the other, therefore 2 peaks. Remember that the environments depend on where they are in the molecule relative to the entirety of the rest of the molecule, not just what they're immediately bonded to. So for 2-methylbutane, aka isopentane, we have 1, 2, 3, 4 distinct environments. 2 of the carbons have the same environment, so we should see 4 peaks. Every chemical carbon environment is affected by the rest of the molecule, but this is what we should find the chemical shift for different environments to be in general. Bear in mind that the height of these peaks does not indicate how many of that carbon environment we have. Hydrogen NMR or proton NMR, however, does give you an indication of how many of each environment we have. Naturally, it's more complicated than carbon-13 NMR. The sample is dissolved in a solvent like tetrachloromethane. As this doesn't have any hydrogen atoms in it itself, it doesn't make any peaks of its own. This is actually used in carbon NMR too, but it just makes 1 peak that we ignore. Now, because the peaks can be split, it's not so much the height of the peak that tells you anything, but rather the intensity of the peak, essentially calculated from the area under the peak. Thankfully, that's not your job to find that, but you're given a number above each peak that gives you the relative intensity. So let's try and figure out what the molecule is from this NMR. We see a peak between 11 and 12, so we can infer that there's a carboxyl group present. We see a peak between 2 and 3, which makes sense, as that would be a CH2 next to the COOH. An intensity of 2 means that there's 2 of these. Finally, we have a peak at around 1 parts per million with an intensity of 3, so that's likely going to be the CH3 at the end of the chain. Not so bad at the moment, but now we look at the peaks being split. Here we go. The hydrogen environment's peak is split as many times as there are hydrogens on an adjacent carbon. That's not the carbon the hydrogen is bonded to, but one carbon over. So if the peak isn't split, that's a singlet. There's no hydrogens on the adjacent carbon. If it's split into 2, there's 1 hydrogen on the adjacent carbon. Triplet, 2 hydrogens. Quartet, 3. This takes some practice, so make sure you have a go at plenty of questions on this and you'll start to notice similar patterns of peaks. For example, a triplet quartet pattern indicates a CH2, CH3. We can analyze what molecules are in a mixture by using chromatography. The particles are pulled up or along a stationary phase by the mobile phase, a liquid or gas that acts as a solvent. The right mobile phase has to be chosen for what's being analysed. They must have affinity. The greater the affinity, the further these molecules are pulled along, or the faster they're pulled along. We measure how far the molecules have moved compared to how far the mobile phase has moved and calculate this ratio, which is known as its RF value, retention factor. We can then compare our measured RF values to known ones to determine what's in our mixture. This is the case for thin layer chromatography. This involves a metal plate coated with a thin layer of silica. The mobile phase moves up that. UV light shows us where the different molecules ended up, and then we can measure the distances and calculate RF values. Column chromatography uses a solid powder as the stationary phase and the solvent used as the mobile phase moves down this. All the different molecules get down to the bottom, but they take different times to do so. So we're actually measuring retention times here instead. Gas chromatography is similar to column chromatography as it uses a thin tube of solid powder again, but this time a high pressure gas is the mobile phase. This is used for mixtures of volatile liquids that are evaporated then sent through, and retention times are recorded. So I hope you found that helpful. Leave a like and a comment if you did, and don't forget to check out our revision app to help you test your knowledge. Links in description.